Hi, I'm Tianqi from Tsinghua University. Today I'll talk about this work on super efficient hash functions and how they can be applied to give us extremely sharp hardness classification and very uniform PRFs. This is a joint work with Li Jia and Zhao Tu. So let's get started. I'll first introduce the result, the unconditional construction of super efficient almost universal hash function. Then I'll talk about how they can be applied to PRFs of low complexity and how they give us sharp hardness classification in the linear size general circuit regime. Then I'll briefly introduce our techniques, how we construct a super efficient hash function. And finally, I'll talk about some open problems. Okay, here comes our main character, the universal hash function. As you may already know, the universal hash function is a family of function collections such that for any pair of distant inputs, the probability of the hash function collide is 2 to the minus output length. Here we view the universal hash as a collection of functions, so the C can be viewed as uniformly selecting a function from the collection Fn. Universal hash function has already found tons of applications in complexity theory. I guess you all know it, so I don't need to mention more about it. But in many cases, we don't need a perfect universal hash function. In fact, for many applications, even an almost universal hash function is enough. And this is what we are talking about today. The almost universal hash function is, instead of having the probability that the hash value collide to be 2 to the minus output length, we only need it to be smaller than some small epsilon. And this relaxation allows us to give very efficient constructions. We'll see. Here, the epsilon is called the collision probability of this hash function, and the logarithmic of the size of this collection is actually the C length. This is uniformly selecting a function from the collection. And we note here that in fact we are considering linear functions. So the linear almost universal hash functions is that every function in the collection is linear. And in this case, you can see that this condition of collision can be written as for every non-zero input x, the hash value is 0 with very small probability epsilon. We are using circuit size to measure the complexity of a construction. This is CCC, so I guess you all know circuits quite well, but I still need to mention this not very common class CC02, which is the constant depth circuits with only parity gates. This is not a complete class since it can only compute linear functions, but it is useful since we are constructing linear hash functions. By convention, when we talk about general circuit classes, we measure the circuit size using the number of gates. But when things come to constant depth circuits like the C02 or AC02, circuit size means the number of wires in it. I need to emphasize here again that the circuit complexity of hash function and also PRFs we'll talk about later is the maximum circuit size in the collection. So this is more like a non-uniform model with respect to the seed. We don't care about the complexity of constructing the circuit from the seeds. Okay, we do care about it. I'll talk about it in a minute, but we don't count them in the circuit complexity. So we want to construct efficient, almost universal hash functions. But before we do so, we first ask ourselves, how can we evaluate the efficiency of a hash function? What are the criteria? As complexity theorists, we of course first worry about the circuit complexity of a construction. And from the definition, we consider the collision probability and the C length. But here are some more. We also consider the output length of a hash function. It tells us how much the input is strong. And more importantly, we consider whether a family of hash function can be constructed uniformly. Say whether it is P uniform or polylog space uniform or something else. That is, whether it can construct the small size circuit efficiently from the seed. And we consider whether the family of hash function is strongly explicit or not. Okay, I haven't even defined the strongly explicit yet, but never mind, you can just think of it for now as something local about the hash function can be printed in polylog time, as things are for the expanders and others. I will define it later. These two, uniformity and explicitness, are essential for our applications in hardness magnification and PRFs. Okay, now let's take a look at what is previously known and what we get in this paper. Here n is the input length and m is the output length. First is the folklore result by an expanded work on an ECC, which can give us an almost universal hash function with collision probability 2 to the minus omega m with the length log m plus little o plus big O m, and it can be implemented in linear size NC1. A very elegant construction is given by Ishai, Kushlevitz, Ostrovsky, and Sahai in 2008 of perfect universal hash functions while preserving the linear circuit size. Their construction needs linear C-length, and this seems unavoidable for universal hash functions. And about the explicitness, they did not mention explicitly whether their construction is strongly explicit or not, but since it is based on the error-correcting code by Spellman, we think it is not very likely to be strongly explicit. Okay, now comes the recent result by Fan, Li, and me, who gave a construction computable by CC02 circuits of size 2n plus little n. It only works for the case of small collision probability. We note here that the collision probability should be at least 2 to the minus omega m. So this collision probability is actually at least inverse cohesive polynomial, since we have a bound here, m is smaller than log square n. But this small collision probability is still negligible, and this very small circuit size is still useful in many cases. For example, we use it to give super efficient construction of PRFs in this FLY paper. Note that this construction is not strongly explicit. One reason is that it has C-length superlinear. You can't expect the unseen printed in polylog time if you need to read a long seed, right? Okay, you can play with the definition and take the seed as oracle access, but still it is not strongly explicit. In this work, we improve over the previous FLY construction. We keep the circuit size to be 2n plus little and CC02, but we reduce the C-length from the original superlinear to be polylogarithmic. In addition, our construction is polylog time uniform. Each edge can be printed in polylog time, and our construction is strongly explicit. I still haven't defined its strong explicitness, but I will define it in a minute. So our hash function is a strict improvement over Fan, Li, and Yang. Compared to the previous two, it can only work for large collision probability. We lose some C-length compared to this ECC plus sampling method, but we still get polylog C-length, and most importantly, keeps the super efficiency of Fan, Li, and Yang. This polylog seed allows us to further give uniformity and explicitness. And this uniformity will be very useful in our later application of uniform PRF construction, and this explicitness will be useful in our application of hardness magnification. Okay, finally I come to define the explicitness. We consider a function in the collection. Since it is linear, it can be written as a matrix multiplication in the Boolean field, right? And what strongly explicit means is that each entry in this matrix can be printed in polylog time if we give you the seed. Alright, so this is our hash function. I'll introduce how we construct it in the second half of this talk, but for now, let's take a look at the applications. The first application is a rather direct one. Within previous almost universal hash function of 2n plus little n, Fan, Li, and me showed a general way to reduce the circuit complexity of pseudorandom functions. For example, in general circuits, assuming the mere existence of PRFs, we can show that PRF can be constructed in 2n plus little n size. If we further assume PRFs in NC1, then the depth can be further reduced to 1 plus epsilon log n. Similarly, if PRFs exist in AC02, then we can obtain PRFs computable by AC02 circuits of 2n plus little n wires. Now, if we plug in our new hash function we discussed previously, we can obtain PRFs of polylog key length and polylog time uniformity. So now, for example, we assume PRFs are secure against some 2 to the n to the epsilon adversary. We can get PRFs of size 2n plus little n with key length polylog and polylog time uniform. Similar things happen at NC1 and AC02. Note that here we have a small improvement on the depths of NC1 PRF, since we are assuming stronger assumption of sub-exponential secure PIFs in NC1. And here is also a small improvement on AC02 on the assumption, also because we are assuming sub-exponential security. You might be confused about the sub-exponential security in the assumption, but I note here that this is in fact unavoidable since we are requiring polylog key lengths. So the security of the resulting PIF is actually sub-exponential. So of course we should assume a exponential secure PIF. And this result improves the previous ones by Ishak, Kuchelevers, Ostrovsky, Sahai, and Viola, and of course our work FL1. Here we sketch how we do it. The main weapon we use is the Levin's trick, which says if some function family f is a PRF, and some other function family h is almost universal hash, then the composite is also a PRF. As seen in this picture, we first have an input string of length n, and first hash it down using an almost universal hash function to an intermediate string of shorter length, then compose it with a PRF construction. In our previous paper, we reduced the input intermediate of length n to the epsilon, but here we reduce it to polylog n. It is possible since our hash has polylog n output bits. The resulting PIF is still secure against poly n adversary because this underlying f is of sub-exponential security. And in such way, the size, the length, and the uniformity of the f below are all polylog. So what only remains to matter is this hash function above, since our hash function has low complexity, small seeds, and polylog time uniform, then so do the resulting PRFs. Okay, now comes the second application, Hardness magnification. But before I do so, I first briefly introduce what is Hardness magnification. It is a recently discovered phenomenon in circuit complexity that in many cases, if one can prove a quite weak lower bound for specific problems, slightly better than currently known, then it can automatically bootstrap to a very strong breakthrough. This is quite surprising and hence received much attention recently since a work in 2018 by Olivera and Sensible. Example: minimum circuit size problem is a problem in MP asking the minimum circuit computing some given truth table. Chen, Jin, and Williams showed in 2020 that if one can prove an omega n to the 2 plus epsilon probabilistic De Morgan formula lower bound for this problem, then n elves is not contained in NC1. This later implication is a big open problem for decades. And we already know an omega n to the 2 minus epsilon lower bound. So this means that if we can improve this known lower bound even a little bit, it is already enough to resolve a major open problem in circuit complexity. Similarly, there's a problem called word problem over S5 that's an n to the 1 plus c to the minus d lower bound for all c greater than 1 in TC0, which implies TC0 is not equal to NC1. And we already know such a lower bound for c roughly 2.41. These results tells us there's a threshold that below it lower bounds are provable, and above it is already enough to imply a big breakthrough. Okay, before going on, I still need to hold a minute and give you some definitions. The probabilistic circuit is a distribution of circuits, and we say decides a language L if its output differs from L with very small probability for every input X. Here, this error probability matters very much, because even doing a standard error reduction costs too much in a small linear size case. We stick to the error probability 1 over poly for its simplicity. And similarly to before, we define the circuit complexity as the maximum circuit size in the distribution. Second, we call a language sparse if for each input length there are only poly n number of yes instances out of all 2 to the n possible inputs. Note that this is stronger than our usual definition of sparse languages. Our definition is, in fact, requires the language to be super sparse. Here's a trivial example. Any unary language is sparse since it has at most 1 yes instance for each input length. We are finally ready to state the results. We show that if we can prove 2n plus little omega n over log n probabilistic circuit lower bound for sparse languages in MP, then we can prove sub-exponential circular lower bound for Nx. And if we only want a polynomial lower bound, say Nx is not contained in P/poly, which is still a big breakthrough, then we can replace this NP by by non-deterministic time 2 to the n to the little o1 time. And if we can prove a similar lower bound for the minimum circuit size problem of some smaller threshold, then we can even improve the Nx in the lower bound to parity P. Here the input to MCSP is the truth table, so the input length is in fact big N. So this lower bound is in fact has a similar form to this above. The proof of this last implication requires a strong explicitness of a hash function, but I won't go into details of why. Now, why is this result interesting? We look at the premise of this implication, and let's compare it to known unconditional lower bounds against general circuits. It is proved by Li and me that there's some language in P that requires 3.1 n minus little o n circuit to compute with. And we know a 2.n minus little n probabilistic circuit lower bound from the average case lower bound by Chen and cabinets. These two are for non-sparse languages. If we further require sparse languages, as we do in the premise, there's a 2n minus 2 probabilistic circuit lower bound. So you can see that even improving these results a little bit, even a second order factor can lead to breakthrough circuit lower bounds. But how should we interpret this result? I always introduce it as we have a big tree, say the breakthrough circuit lower bound Nx is not contained in P/poly, and we complexity theorists are trying hard to cut down the tree, maybe from different aspects. But although we chop and chop, we can only hurt the tree a little bit. So it is natural to ask ourselves, how long on earth will it take for us to cut down the tree? What our work suggests is that the tree is in fact hollow. It only has a very thin shell, and breaking the shell is enough for cutting down the tree. But still, does it mean that we are already close to cut down the tree, since we only need to break the shell? Or it suggests that the shell is made of, I don't know, titanium, so even breaking the shell is really hard? We don't know. We just don't know. There are some efforts made to consolidate these two possibilities. Optimistically, we know this method breaks the natural proof barrier. But on the other hand, we have the locality barrier and the black box natural proof barrier, which suggests that even proving weak lower bounds are very hard. Now let me briefly tell you how our hardness amplification is proved. This proof motivated from work by Tianqi and Williams in 2019. We prove the contrapositive. We assume Nx is in P/poly and we take a sparse NP language L. Our goal is to show that L can be decided by 2n plus little n probabilistic circuits. This is done via kernelization. We consider the whole input space of L, which is 0, 1 to the n. L has some ES instances in this space, and we mark them as red here. And there are only a few red points here since L is a sparse language. And now we hash this large space to a smaller space, say 0, 1 to the polylog n. Now since we use an almost universal hash function and there are not much red points here, with high probability no red points collide in this smaller space. So the red points here in the input space becomes red points here in the smaller space, and since becomes denser since our space is smaller. These red points in the smaller space give us a new language L prime. Now since our original language L is in MP, we show that L prime is in Nx. Then from our assumption that Nx is contained in P/poly, L prime has polynomial size circuit. And this in turn tells us that L has probabilistic circuit of size 2n plus little n. This is the basic ideas of the proof, and you can check our papers for details. And of course, the results for MCSP we mentioned before. Okay, I'll now proceed to give you some technical overview of our hash construction. Our hash construction directly improves over the one in FLY, so I'll first review the construction there, and then tell you how to reduce the seed length and make things explicit and uniform. The main construction of FLY considers the inputs with small and large Hamming weights separately. It constructs an H-light which outputs non-zero with high probability if X has small Hamming weights, smaller than some threshold theta, and it also constructs an H-heavy which outputs non-zero when X has Hamming weights larger than theta. By concatenating the outputs of H-light and H-heavy, we get an almost universal hash function since the output non-zero whenever X has small or large Hamming weights, but it only has output length something like n over log n. We then compose it with an almost universal hash function with a bit larger complexity, but allows us to shrink the output length to polylog. Now we can afford the larger complexity because the input is already shrunk to this smaller intermediate. Here we rely on the fact that the composite of two almost universal hash functions is still almost universal. In FLY, we choose theta to be n to the epsilon, but in this work we need a final choice of theta to ensure the small seed length. We will see later that this H-light part requires all theta bits of seed, so we choose the theta to be polylog n. Now I will lead you through these two components, each of them having some issues on the seed length, explicitness, and uniformity, and I'll discuss how we resolve them. We first consider the simple part, H-heavy. Here we need a family of linear function collection such that for all x of Hamming weight at least polylog n, the probability of fx is equal to 0 is small. This part can be simply done by a sampling. In particular, we sample, say, n over log n number of inputs and directly mark them as outputs. And with high probability, at least a 1 from the input will be sampled, so output is non-zero. This sampling is almost free because we are just marking the inputs as outputs. The only costs are constructing the circuit. But remember, we wish to get good seed length, good explicitness, and good uniformity. How do we do this? In this case, it is quite simple via standard randomization trick, but it is a bit tricky to make things explicit and uniform easily. Here's how we do it. We first partition the inputs into blocks of size log n, so we have n over log n blocks. We then sample one input from each of the blocks and mark them as output. And we do the sampling via an almost k-wise dependent distribution. Now since we are only sampling one input from each block, we have output length n over log n. And since we are sampling via k-wise independent distribution, the seed length is polylog n. Here the almost k-wise independent distribution, we use this strongly explicit, so our hash function is strongly explicit as well. So everything is good. The H-light part requires more work. Here we need a family that outputs 0 with small probability for all x with Hamming weight at most polylog n. At first recall how FLY do this. The circuit we are building is a depth 1 XOR circuit, but there's only one layer of output. Each output is the XOR of some of the inputs. And the circuit is a left-to regular bipartite graph, so each input will only be fed to 2 of the outputs. In such way, we can guarantee that the circuit complexity is 2n. What is hard is to show that it outputs non-zero with high probability. The main observation is that we can identify such a left-to regular bipartite graph as the vertex edge instant graph of another graph, as shown here. So each output represents a vertex and each input represents an edge. And if some input x gives us fx is equal to 0, then it means that each vertex is instant to an even number of ones in the input. What does this mean? It means that it gives us an Eulerian cycle. Now if we define the girth of the graph to be the shortest cycle in it, and if we take the right graph to be of girth g, then in the left circuit, for all x of Hamming weights less than g, the function value should always be non-zero. Why? Because otherwise you have a cycle of length shorter than g. Now we plug in our own explicit high-girth graph construction, and this gives us a non-zero output for all x of Hamming weight at most log n over log n. But our choice of theta is greater than this. we need h-light to handle all inputs of Hemingway up to point log n. The next observation is, for inputs of length greater than g, we still get some structure. If the Hamming distance of two inputs x1 and x2 is smaller than g, then their f value cannot be both 0. Otherwise, the symmetric difference gives a shorter cycle. So we get an average case upper bound on the number of x making fx 0. Say for any t not too large, if we randomly choosing an x from those of Hemingway t, the probability of fx is 0 is very small. Now we randomly permute the input bits. Then for any such x, it is permuted to a random string with the same Hamming weight. So the probability that fx is equal to 0 becomes very small. And this is exactly what we want for h-light. This is the construction of this part in FL1. But there are two issues. The first is that this Hardness graph construction is not strongly explicit. And we didn't find any strong explicit Hardness graph construction explicitly stated in the literature. But fortunately, we are able to construct one from a Hardness graph by Laspnik and Ustimenko, so this part is okay. The second problem is the random permutation here requires too much randomness. But we notice that to argue x with Hemingway t, using a t-wise independent permutation is enough. This is why we set the threshold theta to be point log. We set the threshold theta to be point log, so here we only need to use the point log-wise independent permutation. By using known strongly explicit construction by Kaplan, Noah, and Ringgold, the C length is indeed point log. So you have done with the h-light and h-heavy parts. The complexity is still 2n plus little n, and reduce the C length to point log n, and it is strongly explicit and point log time uniform. Good. But the output length is n over log n, and this is a little bit not enough. What we do now is to stack it with itself for a constant number of times, so the output length becomes n over point log n. Okay, now we go on to this final component, h-shrink. Here, our goal is to use an almost universal hash function with possibly large complexity, but output length point log. We use the hash function in Tianqi and Williams, which is based on an expander walk sampling over the epsilon bias set. The circuit complexity can be trivially bounded as n as O input times output. And since we already reduced the input to n over point log, and we are outputting point log number of bits, the resulting complexity is little n. Good, we are done. So this is the overview of our construction. Finally, I will present some open problems. The first open problem is, can we improve the collision probability of a hash function to exponential by preserving the 2n plus little n complexity? Our current construction is quasi-polynomial, and we don't know how to improve it. For this problem, we don't need to have point log C length, even polynomial one is very interesting. Second, can we reduce the C length to O log n if we tolerate some loss on the collision probability? Our current construction needs around log cube C length even with constant collision probability. Third, can we prove a better than 2n non-probabilistic circuit lower bound for sparse languages? This will complement the Hardness amplification results. So that's all. Thank you very much. You can send me an email if you have any questions.